Today we're going to finish off our unit by classifying our collisions into one of two categories. Okay, we've talked about a lot of different collisions, right? T-bone collisions, glancing collisions. There's lots of different ways we can categorize them. But the main way we categorize them is according to whether it's elastic or inelastic. Now, what's the difference between an elastic collision and an inelastic collision? Momentum is conserved in all of them. Momentum has to be conserved as long as we have an isolated system, right? As long as we have no external forces, momentum has to be conserved. It always is. And we're not just simplifying things for you because you're not smart enough to understand in grade 12. Momentum is always conserved as long as we have an isolated system. Even in fourth year advanced physics in a physics degree, momentum will still be conserved if you have an isolated system, always, no matter what kind of collision we have. But we can categorize a collision based on whether or not kinetic energy is conserved, because sometimes kinetic energy is conserved, sometimes it's not. Sometimes we lose kinetic energy. If we have an elastic collision, momentum, of course, will be conserved, but so will kinetic energy. That means momentum will stay the same, but so will kinetic energy. If we have an inelastic collision, of course momentum is conserved. But this time kinetic energy isn't. You're going to lose kinetic energy in the case of an inelastic collision. Now, this seems like a relatively simple thing, and it is. It is. It's easier than a lot of the stuff that we've done this unit. The good news is you will be asked about the difference between an elastic and an inelastic collision on your unit test. The good news is you will likely be asked about the difference between elastic and inelastic on your diploma exam. That's good news because it's pretty easy if you just remember that momentum is always conserved and kinetic energy is sometimes conserved. Now, the way in which you're asked that question, that varies a lot. It takes one of many, many different forms. But it boils down to, is kinetic energy conserved or not? Here's a little table to summarize. If you have an elastic collision, momentum is conserved. If you have an inelastic collision, yes or no? Yes, momentum is conserved. It always is. If you have an elastic collision, is kinetic energy conserved? Yes, Charles says. It is. If you have an inelastic collision, is kinetic energy conserved? No, it isn't. And that's where we're going to put the X. Kinetic energy is lost. You lose kinetic energy. You never gain kinetic energy, by the way, unless you have an explosion. And if we have an explosion, we're not going to categorize it as elastic or inelastic. So we're always going to either lose kinetic energy or it's going to stay the same. Now, finally, what is this third column here? Objects bounce apart? Well, one of the observations that we can make about a collision is that the objects either stick together or they bounce apart. And sometimes, not always, but sometimes that can actually be helpful in helping me classify it as elastic or an inelastic collision. In an elastic collision, the objects will always bounce apart. In an inelastic collision, the objects will sometimes bounce apart. What we mean by that is this. Two objects hit each other, they bounce apart. You're going to look at it and say, oh, wait, it's either elastic or inelastic. You don't know. Two objects hit each other, they stick together. It's got to be inelastic because elastic, they always bounce apart. So if they stick together, it's got to be inelastic. If they bounce apart, it could be elastic or it could be inelastic. Does that make sense? You ever get a question where they stick together? They ask you whether it's an elastic or inelastic collision. Right away, say inelastic. If they bounce apart, it's probably still going to be inelastic because the vast majority of collisions are inelastic. But every once in a while you find one that's elastic. If you got to guess, hey listen, if you got to guess inelastic because most of them Most collisions are inelastic. But every once in a while you find one where they bounce apart and it is elastic. There are a few situations out there in the macroscopic world, in the everyday world, where collisions are very close to elastic, but not perfectly elastic. There are many situations, almost all situations, where they're inelastic. Let me give you an example of a few of each. Okay, bounce a basketball on the ground. Basketball hits the ground, collides with the ground. That's an inelastic collision. Two cars hit each other. That's an inelastic collision. Two football players hit each other. That's an inelastic collision. Two curling rocks hit each other. That's really close to elastic. Really close to elastic. Two pool balls hit each other. Really close to elastic. What's the difference? What's the difference between those situations? We had, for inelastic, basketball hits the ground. We had two cars hit each other. We had two football players hit each other. For elastic, or at least really close to elastic, we had two pool balls and two curling rocks hit each other. What's the difference there, Kevin? Okay, after they hit each other, still going at the same speed. Okay, but how do we know they're still going at the same speed, right? Okay, good. That's where I want to get there. They don't compress. Okay, it all depends upon compression. Okay, you learned in Science 10, second law of thermodynamics said, first law said, basically the law of conservation of energy says energy can't be created or destroyed. The second law said that you can't even break even, right? In any energy conversion, you always lose a little bit. When a basketball hits the ground, there's a conversion of energy taking place there when the basketball compresses. You're converting kinetic energy of the basketball.
Good morning. I apologize for the interruption. I know we're all busy.
You're converting kinetic energy to elastic potential energy, right? The basketball squishes. You got elastic potential energy. You had kinetic, now you've got elastic potential. And then when the basketball starts going up into the air again, as it becomes uncompressed, you're converting elastic potential back into kinetic energy, and then eventually back into gravitational potential. There's energy conversions taking place there, and every time you convert energy, you lose a little bit. Kinetic energy disappears, usually in the form of heat, maybe sound, maybe a little bit of light in certain cases, usually heat. The bottom line is you lose kinetic energy. That's got to be an inelastic collision. Two cars hit each other. They squish. There's a conversion of kinetic energy to elastic potential. If we have a conversion, we lose energy. It's got to be inelastic. Two curling rocks hit each other, on the other hand. They don't do much squishing, right? They hit each other, they bounce off. There's not very much squishing there. There's not very much of a conversion of kinetic to elastic potential. Therefore, if there's not very much of a conversion, there's not very much kinetic energy lost. Therefore, it's pretty much going to be an elastic collision. The only truly elastic collisions, pool balls are close. Curling rocks are close. The only truly elastic collision are subatomic particles. Anybody explain to me why they would be perfectly elastic? Particles that are, John, were you ready to raise your hand there? Yeah. Particles that are subatomic are as small as they get. You can't compress something that's as small as it gets. And if you can't compress it, you can't convert kinetic energy to elastic potential energy, and therefore you're not going to lose any energy in the process of converting. So subatomic particle collisions are truly elastic. Some other collisions are almost elastic. Most collisions are inelastic because there's some compression involved there and some conversion of kinetic energy to elastic potential energy. Make sense? All right. How do we, black and white, determine whether a collision is elastic or not? Okay, how do we, even if we don't remember when they stick together, they bounce apart. Even if we don't remember they compress or don't compress. How do we determine whether a collision is elastic or not? Well, let's calculate the initial kinetic energy. Let's calculate the final kinetic energy, and then let's just compare them. If they're the same, it's elastic. If they're not the same, it's inelastic. Right, Mason? We're going to call this object, object number 1. We're going to call this object object number 2. Object number 1 is moving initially at 0.500 meters per second. Strikes a stationary snooker ball, so we're going to say V2I is 0. And the billiard ball, the 0.16 kilogram ball, rebounds at 0.0230 meters per second to the south. That's going to be V1F. Object number 1 after the collision takes place. But I'm going to circle the north and the south there in red, right? Because I don't want to forget that one of them is negative, one of them is positive. The snooker ball, that's object number 2, moves off with a speed of 0.465. We're going to call that V2F. Is it elastic or inelastic? What's your guess on this one? What's your guess? Elastic? Why? Why elastic? Okay, if they bounce apart, it could be elastic, it could be inelastic. If they stick together, it's got to be elastic. It's got to be inelastic if they stick together. Okay, so we know they bounce apart. We know at least it's got a chance at being elastic because they bounce apart. Now, Kirsten said that they're not going to compress very much, so that means they're probably going to be elastic. Okay, if we ever see a problem where in the everyday world where we're going to have an elastic collision, then this would probably be it, because those billiard balls aren't going to compress very much, right? But we still got to crunch the numbers just in case. If they stuck together, would we have to crunch the numbers? No, because we know it's inelastic then, right? If they bounce apart, we have to see whether kinetic energy is conserved or not. Our guess is it will be, but we don't know for sure. Okay, let's calculate EKI. By the way, don't do this. Don't set EKI equal to EKF. How come? We did it with momentum, right? Why not, Andy? Yeah, we can't assume it's the same if we're trying to determine if it's the same. With momentum, we already knew it was the same, right? EKI is equal to 1/2 m1 v1I squared plus 1/2 m2 v2I squared. By the way, even if the masses are the same, don't cancel them here because it doesn't appear on the left-hand side. The second object has 0 velocity before the collision, so we're just going to say it has 0 kinetic energy. 0.5 times 0.16 times 0.5 squared gives me 0.02. How many digits should that be rounded to? The number of digits is important here, really important. You'll see why in a minute here. How many significant figures? 3. So 0.0200 joules. You'll see why in a minute. It's very important. Okay, let's get EKF. 1/2 m1 v1f squared plus 1/2 m2 v2f squared. Hey, have I missed something here? Have I left something out, Andy? Should be a negative 0.0230, or should it? If you square it, it becomes a positive, okay? But strictly speaking, you shouldn't even put the negative in there to square it, because this is 1/2 mv squared. What does v stand for there, Andy? No, speed. With momentum, it was velocity. We needed the sign. When it's kinetic energy, it's a scalar. We don't only not need the sign, we don't want the sign. Got it? Hey, if this was a two-dimensional question where it was 0.0230 at 27 degrees south of west, we put in 0.0230. Drop the angle. Don't ever solve a kinetic energy as a two-dimensional problem. Don't ever break a kinetic energy problem up into x and y components. Don't ever include direction for kinetic energy, whether it's a negative or whether it's an angle. Just forget about direction entirely for this question. This question would be no harder if there was 3 angles in there. It would be exactly the same if there were 3 angles in there. Okay, let's get the value of EKF and see what it works out to be here. Say 0.5 times 0.16 times 0.023 squared. Let's add that to 0.5 times 0.18 times 0.465 squared. To 3 digits, it's 0.0195 joules. Oh, yep.
When we're doing our calculations, should we leave them unrounded or do you want us to round?
No, don't round before the final answer. Okay, so I just put it all into my calculator at once, and then I didn't have to worry about rounding, right, until the end. But when you square this, you're going to get some crazy number, right? Leave it in your calculator, okay? Especially when you're dealing with two numbers that are this close together, that becomes pretty important, actually. Is this elastic or inelastic? Kirsten, elastic or inelastic? Elastic? Who says elastic? Who says inelastic? I'm going to say inelastic. Oh, it's so close. In fact, if you rounded it to 1 digit, it would be the same number, right? Rounded to 3 digits, it's not the same number. If we rounded it to 1 digit, we'd say it's elastic. 3 digits, it's inelastic. How does that work? Well, how do we know to round it to 3 digits? Because that's the rules of significant figures, right? That's why it's important to round this to the correct number of digits. If it's that close, okay, you got to go to the right number of digits to determine whether it's elastic or not. So Kirsten, we'd say for this one it's inelastic because you have kinetic energy lost. Very, very, very little kinetic energy lost, but still kinetic energy is lost. Could be. Yeah. On a diploma, the numbers could be that close. That was the question. What you won't find is that you're not going to find them much closer, I don't think. But bottom line is, Kirsten, you have to know how many digits to round it to, and you have to round it to that number. And if you round it to, if you do it, round it wrong and round it to 1 digit or even 2 digits here, you're going to say it's elastic, right? But if you round it to the correct number of digits here, 3 digits, then you're going to say, oh, it's a little bit less. Doesn't matter if it's a little bit or a lot, it's still inelastic. Got it? All right, here's your homework for the weekend. Not a ton. 2 questions on page 482. Remember, drop the directions. I don't care whether it's left or right or up or down or north or south. I don't care whether it's 26 degrees north of west. Okay? Don't break it into x and y components. Don't include negative signs. Don't include angles. In addition to these 2 questions, you've got a little mini assignment to do. And I'll hand that out to you in just a second. The little mini assignment is 8 multiple choice and 2 numerical response questions from all over this unit. Okay, from the very beginning of this unit to now. I want you to do those 10 questions. Even though they're multiple choice and numerical response, I want you to show your work for those 10 questions just beside the question. It doesn't have to be particularly well organized or particularly neat. I just need to see that you've done it. And then on the front page, just bubble in your answer. Right?